Philosophy, Chapter 3, Introduction to the Atmosphere, and I'm Dora Bradley. We're going to talk about the atmosphere today, and the components of this chapter will be the size and composition of the atmosphere, the composition of today's modern atmosphere, the vertical structure of atmosphere, and the human-induced atmospheric change. Our last chapters will be on weather and climate. The size and composition of atmosphere deals with this wonderful blanket that insulates our Earth. It wraps itself around the Earth. It holds in the temperature that we have, which is one that is exceptionally livable, and blocks out that is intolerant. It cushions it. It keeps it cool enough and warm enough without exceeding exceptional temperatures. It holds in all of the gases that make up our atmosphere, which makes our all living beings being able to live and breathe. It's around us uniformly, and it stays in place. It's held down by Earth's gravity. It has a certain amount of weight. It has a amount of air pressure that is held in place by that gravity. And it helps that we have the Earth's gravitational pull, but it's not so tight that we can't live and breathe and move, and it is not held in place, and it's constantly moving. The atmosphere itself extends outward over 10,000 kilometers. However, most of that, 50% of the atmosphere's mass, is concentrated in about 6 kilometers, or about 3.8 miles above the surface of the Earth. 98% of this extends all the way to 26 kilometers, which means that above that 3.8 miles where you and I live and breathe, the air is fairly thin. Only 48% of this atmospheric mass extends further than that 6 kilometers up to about 26 kilometers. So between 3.8 miles and 16 miles, it's only like 48% of the atmospheric mass, while below that 3.8 miles, it's 50% of the atmospheric mass. We also have to think that it extends downward into caves and rocks and soil in the interstices that are just tiny spaces, and it dissolves in water. It dissolves into water, into the bloodstreams of living organisms. Today's atmosphere is nothing like it was in the very beginning of the development of our Earth. About 4.6 billion years ago, the Earth's atmosphere was mostly hydrogen and helium. As it gradually grew, organisms and bacteria were able to take this helium, living off this helium, digesting whatever byproducts that were in the oceans, and they would expel water and carbon dioxide. And so this water and carbon dioxide came to form the oxygen that we also live and breathe today, the byproduct of those single-celled bacteria that were living off of the products of the Earth and digesting it and expelling oxygen, which O2 and CO2. So our atmosphere was definitely influenced by life that was in existence on Earth and evolved as it went on. There are two primary gases that make up our atmosphere. We have the permanent gas, which is oxygen and nitrogen mostly, with a few other particular types of gases that are intermingled. Those are the variable gases. They include water vapor, carbon dioxide, the ozone, and some variable gases. Nitrogen makes up about 78% of the air. Oxygen is only 21%, but that 21% is definitely important. Argon is in existence in 1%, while neon, helium, methane, krypton, and hydrogen are found in trace amounts. So if you added up the 78% nitrogen and the 21% oxygen, you would come up with 99%. So there is just barely enough of those others to make up the remaining 1%. Variable gases include water vapor, which if you walk outside, you're going to sometimes feel it more days than others, especially on wet, humid days. It's invisible on the Earth's atmosphere except whenever it becomes exceptionally dense and you can see the particles, the water particles in the air. But it determines the humidity of atmosphere. It's the source of all the clouds, of all the precipitation. It's stored in different forms. It can be stored in the gaseous state in clouds, and usually it is moving in some form and responds to various forms of heat or cold. It may be as much as 4% of the total volume of the air over warm, moist surfaces, such as our tropical areas, but it could be as less than 1% over arid areas. And the total amount of this water vapor in the Earth's atmosphere is usually constant. So it's a variable in its location, not in its time. Carbon dioxide is only water vapor and carbon dioxide have a significant effect on weather and climate. And carbon dioxide, we know, is one of those byproducts of most living organisms that are breathing. Then one of their byproducts will be a carbon dioxide, but it is usually cleaned in the photosynthesis process, and so we have a release of other gases as a result of photosynthesis. Water vapor and atmospheric carbon dioxide significantly affect the climate because they can absorb infrared radiation and they keep the atmosphere a bit warm. Now, the proportion of carbon dioxide has been increasing at about a rate of 2 parts per million per year, and as at present, it's at 396 parts per million. And there is more details about this in our textbook. We go on and we talk about the ozone that's in the air is a molecule. Ozone is a molecule made up of 3 oxygen atoms, and that's all that's in it is oxygen, 3 oxygen atoms. And it's mostly concentrated in our ozone layer, which is in the stratosphere. Usually that's between 15 and 48 kilometers above the Earth's surface. And it helps to absorb ultraviolet, deadly ultraviolet solar radiation, and that protects human life and animal life. The proportion of carbon monoxide and sulfur dioxide and these other chemicals is also increasing from emissions from factories and from cars, and this is where we're going to be talking about anthropogenic climate change. All of these are hazardous to life and they may affect our climate. Methane is introduced naturally by decaying animals, by our digestion systems. It's also anthropogenically introduced and it absorbs the long wave radiation, which kind of leads to greenhouse gases. Carbon monoxide and sulfur dioxide, nitrous oxides, and hydrocarbons are also increasing, introduced by anthropogenic sources. Particulates are considered those particles that exist in the air that are not gas. They are dust particles. They are sometimes different kinds of broken down particulates. They're hygroscopic. They absorb water, and the water vapor usually collects around them. This is kind of important in forming of clouds and further forming of raindrops. So they do have a particular aid to our climate. However, they can be harmful in the fact that you may be breathing some harmful particulates. They either absorb or reflect sunlight, and so they decrease the amount of solar energy that reaches the Earth's surface. So in a way, a second thing they can do is to keep our Earth from overheating if they're in the right location. This particular slide that you're looking at is showing a dust storm, which is not a healthy thing. And of course, if you were in a dust storm, you would definitely want to cover your mouth and seek shelter, because it would infiltrate your lungs and probably choke you to death. Now, there are structures to our atmosphere, and on this slide that we have and this is also in your book if you can turn to that page. There are four major divisions, but there are also some smaller areas that are dividing areas. The lowest level is the troposphere. The troposphere is the lowest 10 to 15 kilometers of the atmosphere. Most of our weather occurs here, and the range, of course, depends on your latitude, your altitude, and the specific conditions that are relative to the continents. We have extreme weather. We have extreme winds. There are turbulent winds. There are doldrums. There are exceptionally dry periods. All of that is taking place in the troposphere. I like to think of the tropics and trope as being my key, that it is the area where a lot of weather takes place. The layer of the troposphere extends upward, we'll just say the first 6 miles. Then above that first 6 or 16 miles, between 16 and 30 is your stratosphere, where there's basically static air. It is where most airplanes fly. There are you're right above the clouds, and the temperature is going to range on average between 51 degrees Celsius all the way up to about 90 degrees Celsius. It is the stagnant air layer. The mesosphere, like the stratosphere, also can be considered somewhat of a important layer, because there are certain features, the ozone layer and all of that can be in that area. The stratopause is the top of the stratosphere, and it's just a little line about right at 48 kilometers where the maximum temperature is reached. Above the stratosphere, from 30 to 50 kilometers, is the mesosphere. There is an atmospheric layer above the stratopause where the temperature decreases with height up to the top of the mesopause, just like it did in the troposphere, and it drops down again to negative 84 or somewhere thereabout on average. The mesosphere is usually considered the middle, and it's a transition zone of sorts that transitions from the stratosphere to the thermosphere. The thermosphere takes its name from temperature because it has the extreme temperatures at its lowest level, around 50 to 60 miles, it is in the average of negative 84 degrees Celsius, and at its upper level, around 130 miles above the Earth's surface, the temperature tends to drop down to raise all the way up to about 180 degrees temperature. This is also where you have the aurora borealis, because there are certain particulates that are in the air that are breaking apart light, and it's fracturing the light, which it causes the aurora borealis to light up the skies. Usually those are the yellows and the reds of the visible light that is being broken and fractured, so that we see those aurora borealis lights, the northern lights. It's in this area the temperature remains relatively uniform as it rises all the way up to the top for several kilometers right above the mesosphere, but it drops, it rises dramatically as it gets all the way up to 130. Now, that's when we enter into the exosphere. Now, the exosphere is the highest level. There's not a lot known about this part of the atmosphere, except that this is like the exoskeleton of a bug. It's just the outer coating. It just kind of peters out, and all of a sudden you are in the interplanetary space in that area. Air pressure. Air pressure is basically the weight of the overlying air. And so the pressure is usually the highest at sea level, and it rapidly decreases the higher you go in to the atmosphere. And if you look at your chart, you'll notice that it shows at 0, which is sea level, that the air pressure extends upward of as again at sea level, the altitude of 0, it's measuring right at 100% of the sea level pressure, and then as you rise up to right below 8 miles, it starts dropping, and it drops all the way to 10%, and then as you get up even higher to about 24 miles into the air, it starts becoming so low that it's registering less than 1%. It decreases with height at a kind of a non-constant rate. The low levels are compressed by the air above, so the surface pressure is much, much higher than before. And of course, it says 90% of the atmosphere is in this lowest 16 kilometers, or about, it shows on here, about 7 miles on this chart. The composition of this structure, the vertical structure of our atmosphere. On the chart that we're showing here, the exosphere, you can see at the very top of the chart, followed by the thermospheres right below, the mesosphere, the stratosphere, the troposphere. All of those consist of the different layers of the atmosphere. But you'll notice that in the middle of this chart, they have combined the troposphere, the stratosphere, and the mesosphere into one unit, and this is called the homosphere. It's the lowest 80 kilometers, and it is considered homosphere because the gases are somewhat similar of what you and I live and breathe on in the troposphere. It is similar in the stratosphere and the mesosphere, the same contents. But as you get above the mesosphere into the thermosphere, you start having a change. And so they call this the heterosphere, which means they have different types of gases at different levels. So right at 50 miles, you start having mostly nitrogen. And that changes at about 65 miles to mostly oxygen, a layer of just oxygen. Then at about 80 miles, you'll have a layer of helium. And then at about 93, 95 miles, you're going to start having a layer of hydrogen. That is the heterosphere, because each one of these layers is a different gas. Now, if you'll also notice that on the very far right on this chart, it shows you that the layer of the ozone layer is lying within the stratosphere, and it's not right above the troposphere, but a little bit higher into the stratosphere, about right at the 15th or 16th mile above the Earth. And that is where it's at 15 and somewhere between 15 and 48 kilometers. They call that the ozonosphere. And that is the area where the harmful UV rays are blocked. And so it's kind of important that that ozone layer stay in existence in that location. Now, if the ozone falls closer to the Earth, you'll have a problem, because the lowest area where ozone lives turns out to be somewhat dangerous for human beings and their abilities to breathe. And so every once in a while, you're going to be finding that we have bad days for ozone, and there'll be an ozone watch. The ionosphere, you can see, which is in the thermosphere, usually lays somewhere between 90 miles and about 120 miles. Or if you were looking at it, it looks like it's 140 kilometers to about 180 kilometers on this chart. And the ionosphere plays a important part in the fact that it has charged molecules and atoms, and in the thermosphere, it aids in long-distance communication by reflecting radio waves back to Earth. And that is it is the key to the reason we have the auroral displays, because that's where the visible light is being broken down and you can see it. So it is also the layer where we get different frequency radio waves and that sort of thing for communication. Now, this slide is dealing with human-induced atmospheric change. We have in this area introduced different types of impurities that end up in the air. And they are often rising at a somewhat rapid pace because they are lighter than most of the air, which is heavy enough that it is being held down in place. And so as it rises up into our stratosphere and can mix with the gases in those areas. It's definitely received a lot of attention in the last 30 years, last 20 years for sure. And mostly because humans are introducing different types of chemicals into the area. Pardon the interruption. We were just talking about human-induced atmospheric change and how there have been introduction of impurities into the atmosphere at a very rapid pace, mostly through different kind of chemicals that we used, automobile and industry, pollution from exhaust and that sort of thing. It has received a lot of international attention in the last 30 years, and as a result, we have seen some reduction in the number of chemicals that have been placed into the air. And so that is one of the things I do have some data on, that it is decreasing. However, how do CFCs affect our air quality, or the ozone layer in particular? Okay. In the chart, and on the upper right-hand side of this slide, you'll notice that there are ultraviolet rays that are coming from the sun and striking a chlorofluorocarbon unit molecule, and it breaks off one of the chlorine atoms. Now, where does chlorofluorocarbons come from? It comes from the breaking down of gases such as freon. Freon was also known as R22, and it is the gas that was in air conditioners. It was not only housing air conditioners, but car air conditioners. Also ran the cooler that froze the ice for the Bowman Ice Arena that was in South Little Rock on Bowman Road for a number of years. But anyway, that refrigerant, as it broke down, it would leak into the atmosphere. And so Freon was like the #1 bad guy. But you also had it in hairsprays. You also had it in other kinds of cans that would have aerosols. And so the good thing about it was that it would keep your liquid and that was in the can and help it to become a spray as we were spraying. And so we used to use hairspray with abandon. And then we mostly changed over to squirter type bottles for hairsprays. But they also changed out air conditioners, so they no longer used the Freon, but a different type of refrigerant. But anyway, that's where the CFC would come from. It was called a chlorofluorocarbon. One of their molecules could bounce into a chlorine atom, and it would break off, and it would have a chlorine atom that would break off and join onto the ozone molecule. It would pull off an oxygen atom off of the ozone molecule, and so you would have one chlorine atom and one oxygen atom floating together in tandem. It wasn't too bad because it would release the oxygen, which was an O3, and turn it into an O2, which is, breathable oxygen. But it would later, as it broke down, the oxygen would become a free atom and be floating out into the air, and that oxygen, that chlorine would continue to go and grab another oxygen atom molecule and break it further apart so that there were just independent oxygen atoms floating around, and it was continuously breaking down more ozone as it went. So it would join onto a chlorine. It would break down, the chlorine would fall apart, it would join onto an ozone molecule, grab an oxygen model, and continue on, later releasing it, going back and grabbing another ozone molecule. And so one of those chlorine atoms could break down a number of ozone molecules, which then would allow a bit of shortwave radiation to be able to leak through. This depletion of the ozone layer, usually the ozone is produced naturally in the stratosphere, and it serves to protect life on Earth by shielding it from the ultraviolet rays of the sun. And so whenever they're broken down, we're absorbing more ultraviolet rays. Now, ozone molecules can be broken down naturally by UVB and VUC rays, radiation, and that releases oxygen molecules and a free oxygen atom naturally. However, this breakdown was becoming excessively fast. About 90% of the atmospheric ozone is, in the stratosphere, and so this prolonged UV radiation, which was being starting to enter into our atmosphere was causing more skin cancer. It was suppressing our immune system. So today you'll see that there are numbers of people that are running around who have been suffering from skin cancer, and their autoimmune system has been breaking down. It also has diminished some of our crop yields. It's killed some of the microscopic plankton on the ocean surface, which often is one of your producers of oxygen. And so it can be harmful to vegetation, and can corrode buildings. And so it's been one of those things that we have been working on to stop this breaking down, because it is causing a hole in the ozone layer, which is located somewhere over the Antarctic mostly. And if you look at the holes and compare them over time, this release of the CFC has resulted in these giant holes growing. On these screens that you see over to your right, the healthy ozone are usually the yellow and the red layers. Green is not bad, but the blue and the purple or violet colors tend to be the harmful areas where they have broken down and there is a lack of ozone. And so this resultant UV intensity has increased, and especially over the Antarctic areas. The Montreal Protocol, which dates back a number of years, 2009, started nations thinking about what they were doing. And at first, whenever they first started talking about this, actually it was in the 1990s, people started voluntarily changing over to different types of coolants for their air conditioners, and changing away from the hairsprays. There were some EPA regulations which made it mandatory, and as that happened, the ozone depletion has changed a great deal. As I said, the chemicals that are found in the air have decreased. The ozone they call it ozone defecting, or types of chemicals. Air pollution, of course, has been a major issue, and of course lately we've been studying it, and there is a lot of debate over whether it's accurate or not, the data is accurate or not, or that the outcomes are accurate. Smoke has been recognized for pollutants in several countries for centuries. I mean, even back in 1300 AD, London proclaimed that the burning of coal was prohibited. Of course, it's come and gone over the years, because coal has been one of those very important energy sources. But over time, it became exceptionally important, especially in the Industrial Revolution, and in all of the places where it's been introduced, starting even as early as the 1700s, as a energy source for factories. It's been found that it causes more human deaths, lung problems, different kinds of illnesses that people tend to go to get. And it usually has been found more in occurrence where there's a greater number of people and automobiles, as well as the use of coal. So these chemical impurities in the air have had a major impact on the pollution. Pollution itself is just dirty air. It's anything that's in the air that causes contamination to our air. And it includes particulates, sulfur compounds, nitrous compounds, carbon dioxide. And so usually when we think about it, those are our primary types of pollutants. those basic particulates, the small particles from dust, especially from smoke, carbon monoxide, nitrogen compounds, and the sulfur compounds. Um, so the secondary pollutants are not released directly into the air, but they usually are from a chemical reaction. And so we call them secondary pollutants. And that's usually something that, like smoke that has bonded with water and other chemicals that are being ejected from the smoke, acids and that sort of thing that are used in processing paper, processing different factory products, cause a photochemical smog in the air. And so these are chemical reactions and processes that are taking place after the fact. And so people generally just call it smoke. We also have indoor pollutants, and you and I probably don't even realize how hazardous some of the indoor pollutants are. Whenever we are spraying cleaners that are in our bathrooms, we're letting out lots of different kinds of chemicals. I had a friend who even died because he was mixing bleach with some other kind of chemical like Purex, because the two together had a different type of a bleaching agent, and they together formed a poison, and he died almost immediately upon trying to just clean his bathroom so that he could move from one apartment to another. And so those are, things you can think of as being our indoor pollutants. Nitrogen compounds or nitrous oxide can form naturally as a byproduct of biological processes, breaking down or decaying of the body or the body feces. It can also form from high temperature and high pressure combustion. If you're blowing up something, nitrous oxide can react to atmosphere to form nitrous dioxide, which is a corrosive gas, and it gives off a polluted air, a yellow or reddish brown in color. It can also react with sunlight to form several different components of smog. So you're thinking, oh, well, it's just smoke, and then the sun comes in and it hits with the sun, maybe even with rain, and causes acid rain. Sulfur compounds are some of the worst. Most are natural in origin from volcanic eruptions, hydrothermal vents, and hydrosulfide is one example. Human activity during the past century has increased the release of sulfur compounds because we're burning fossil fuels in our cars, and these compounds have sulfur dioxide in them, and so whenever they're in the air, they are going to react with the atmosphere and form sulfur trioxide and sulfuric acid. Particulates are little tiny particles of droplets that are usually coming from dust and smoke of industrial combustion. The particulates concentrate may increase through those secondary processes where they're bonding with other chemicals. The health hazards arise when particulates are in the level of 2.5 micrometers in diameter, whenever they're getting larger. In 1997, the United States Environmental Protection Agency, the EPA, revised its regulations to take into account the harmful effect of such fine particulates. Photochemical smog is the next thing that we have to think about. And so a number of the gases react to ultraviolet radiation and strong sunlight, and they produce secondary pollutants known as photochemical smog. Nitrogen dioxide and hydrocarbons, also known as volatile organic compounds, are generated from incomplete combustion of fuels. Now that says incomplete combustion of fuels, and they're major contributors. Nitrogen dioxide breaks down under UV radiation. We've talked about that before, and forms nitric oxide. And then they react with those volatile organic compounds to form a peroxidal nitrate. and this has been a significant cause of crop and forest damage. They can also form ozone on the earth level, which is a main component of photochemical smog. The components, conditions within this atmosphere can also determine the air pollution levels. Stagnant air can cause pollutants to accumulate in a region, and so it's more dense in its numbers, while rapid and frequent movement from winds will allow pollutants to be more readily dispersed. And so in a way, it's almost thankful that we do have some winds that are coming through. Consequences of this air pollution from anthropogenic sources is carbon monoxide, sulfur dioxide, and they contribute to cardiovascular disease and lung cancer. Nitrous oxides are principal contributors to acid rain. And acid rain, when it falls, it kills trees and forests, and it's one of the major killers of forests in Europe. The tropospheric ozone damages crops and trees and is now most widespread air pollutant. And so the EPA reports that about 1/5 of all hospital cases involving respiratory illness in the summer are consequences of ozone exposure. The last few decades, there has been a downward trend in emissions of pollutants, except with nitrous oxides, which does acid rain, and ozone. And these are the most because increasingly stringent emission standards that have been imposed by the EPA. Now, energy production. The release of CO2 is still on the rise despite reductions of air pollutants, and much of this increase challenges that are associated with it from the production of energy. Now, here in this picture, you'll see some of the consequences of anthropogenic pollution. You can see the smog. This is like over Los Angeles. Now, Los Angeles happens to lie in an area where air is trapped because of the different air pressure and winds that tend to blow over mountains don't sweep down into their valley. And so you have what we call a temperature inversion, where this air is trapped below the higher air levels, and it can't evaporate, it can't dissipate. And so it causes even higher levels of damage to human lungs and that sort of thing. Weather and climate. It's going to be another one of our topics. Weather is the short-term atmospheric conditions for a climate area, while climate, on the other hand, is a long-term collection of data regarding weather conditions. So it's weather over a long period of time. And whenever scientists are studying weather, they usually take several decades of weather, and then they'll average out the data to come up with a determination of classification for the climate of an area. Meteorology is the study of weather on a short-term basis, and so whenever you're watching the news at night, you're watching this short-term information about what the weather is going to be tomorrow. Well, climatology is the study of climate over the different decades. And so we know that weather is changeable. It varies from day to day. However, it usually seems to fall within the guidelines of whatever season you have in a particular area. The climate, on the other hand, is usually a long-term average. So if you're going someplace and you need to know whether to take a coat, you're going to be looking at the weather. While if you want to know whether you want to move to a certain area, you probably want to look at the climate. When I moved to Minnesota, I didn't know that they had snow on the ground for several months out of the year, and sometimes the snow would be as deep as 7 feet. that the temperature, like in December and January, the average was 10 to 20 degrees below zero, and it would stay that way for a whole month, maybe two. So that is more climate, and it was something that was predictable because of previous summers. While weather from the day to day, yes, you would have a sunny day. One day you would be running around in the 70s degrees in Minnesota, and the next day you might be having a blizzard that was coming through. On the right-hand side of this slide, you'll notice that these are the different elements of weather: the temperature, pressure, wind, and moisture. And all of these tend to work together to form our weather on a short-term basis. The controls of weather and climate are listed on the right. And I have often drawn, and I probably should be drawing, some sort of a small chart for you to talk about latitude and distribution of land and water and all of that. But I think we're going to be talking about these on these next slides. But if you will think about it, if I were to ask you, what are controls of weather and climate? These are the features that tend to make the determination of which ones of the elements of climate that are going to be in effect. So the controls are going to determine which of the elements are in effect. So when they talk about latitude, you and I know that Minnesota, being on a farther north latitude than Arkansas, that the weather tends to be cooler in that area. And so you can pretty much determine that most cities that are on the same latitude are usually generally going to have the same kind of average temperature, because that is, depending on the season, because that is the angle of the sun, the sun's angle on hitting the earth. Latitude is the influence of the temperature and the basic function of heat over the earth from the sunlight and the amount of it that is hitting on a particular latitude. Now remember that on the equator, from the equator to the tropics, usually they're getting more of a direct ray, and so their temperatures are going to be warmer, while in the north we're going to have a cooler temperature because we're getting an indirect amount of sun's radiation. We also have the amount of water that is in contact with land. If you're in the middle of a continent, you tend to lose heat and increase your heat at a further direct amount. It will be more dramatic. You will have a dramatic increase and a dramatic loss. So like in the middle of the day, you'll heat up really warm. At night, when the sun is gone, you'll drop in temperature. Well, that amount of change from the highest point of temperature to the lowest amount of temperature is going to be greater in areas where there is more land mass and you're further away from oceans. Oceans tend to insulate coastlines, and the weather tends to be milder. You'll have a slower increase in temperature and you will have a slower decrease in temperature because water increases and decreases its temperature at a slower rate than land mass. So Kansas City, being on the interior portion of the United States, is going to have a broader amount of temperature change, as is any place in Minnesota, while Seattle on the coastline, or San Francisco, is going to have milder temperatures. San Francisco being about on the same location latitude-wise as Kansas City, San Francisco is going to have a milder temperature. It will not, over the whole year, it will have a very mild change. The range in its temperature will not go as high, it will not go as low as in Kansas. Seattle will have a mild temperature. It will not go as high or as low in its temperature during the day and nighttime changes as it changes in Minneapolis or South Dakota, North Dakota. And so a lot of that has to do with the amount of water that is close by and insulating. These maritime climates also usually are more humid, and whenever you have humid air, it tends again to act as a cushion or a blanket to maintain the stability of that climate. General circulation of the atmosphere usually is controlled by a semi-permanent wind pattern on the Earth. And if you look at this chart that is on this slide, I believe your slide number may be slide number 18, you'll notice that the winds along the equator inside the tropics blow from east to west. And part of that is because the Earth is turning from west to east. Along the equator, you'll feel this change most in the fact that the winds blow east to west. The Earth turns along the equator from west to east. The winds blow from east to west. And so they're going to be calling those the easterly winds, and we'll talk about those later. In the middle latitudes, it changes directions. And we'll talk about the reason that does that later. And so the winds will blow from west to east in the mid latitudes. And it will change again in the polars. In the polar regions, it will blow from east toward the west. And so they call these general circulation of atmosphere or the semi-permanent wind patterns. The circulation of oceans are also affected by this same movement. You'll notice that along the equator, the ocean's currents will move from east to west, and as they bump up against the continents and can't move very much further, they are pushed further away, and they tend to move in the northern hemisphere. They'll move to the right. They turn to the right, which means that they're going poleward. They will start moving up the coastline poleward, and then when they get in the mid-latitude along the 30th degree lines north and south, they will turn back eastward. Again, they'll flow eastward until they are butting up against the coastline, and they'll follow the coastline back toward the equator, and then they'll join up with other currents again at the equator and move again from east to west. And this is the oceanic broad-scale semi-permanent motions. And they call this ocean circulation the general circulation of the oceans. So altitude or elevation is one that influences, because as you're moving up the side of a mountain, you will find that the trade winds are butted up against different landforms. And not only trade winds, but winds in general butt up against wind forms. And so there will be some changes that will be produced. That's altitude and elevation. If you go up a mountainside, you'll notice that the different levels will have changes in their weather and their climate. You may, at the bottom of a mountain in Quito, Ecuador, which is right on the equator, you'll have a tropical type of vegetation. And as you move up the side of the mountain, you'll find that you will have a kind of mid-level type of plants like you would grow corn, you could grow rice, and maybe some other vegetables. The higher you go, you would produce more root types of plants like potatoes. And then at the top, you'll probably not be able to grow anything because at a certain level or tree line, you will not be able to have any vegetation grow at all. And so that is altitude. The reason for this is that as we move up in altitude, if you remember on the charts, most of the density of atmosphere is at the bottom. And so that dense area is going to maintain certain water moisture levels, and the air pressure will maintain the heat of that area. But the air gets thinner as you move up the mountain, and so as the air gets thinner, the air starts losing its temperature, and the molecules start cooling off and spreading farther apart and becoming less dense until you get up to the top where it's very, very thin. So altitude has a major control. Topographic barriers, of course, whenever the trade winds or other types of winds run into mountains, they're bringing moisture with them. They're moisture laden. And so whenever they hit that area, they start being pushed upward. And just as the plants are affected by the temperature as it goes up a mountain, water also is affected because it starts to condensate when air rises into cooler levels of temperature. And so then once it condensates, it starts dropping its moisture, and it will drop most of its moisture at the base of a hill, continue climbing, and even pull away moisture at the top of a hill. And so you'll have lush green tropical growth at the bottom of the hill. You'll have more cactus and dry type at the top of the hill, or even on the other side of the hill. And so you'll have a rain shadow that's going to be on the other side. Now, one of the things that they don't include in the factors of climate and weather are storms. Storms tend to pop up and can be somewhat erratic and unpredictable. Yes, they do usually follow the patterns of the directions of the wind circulation, the atmospheric circulation. So you can kind of predict which direction they're going to be going, but on the whole, timing is the thing that it often is the thing that you can't plan on. And of course, it depends on how strong the winds are, how fast it's moving, which direction it's going to hit. And so if it has a lot of energy and it's going at a very high speed, and you can predict that to continue, you can guess about where a storm is going to occur. However, if a storm is over water, it's picking up lots of moisture and it has a lot of power and potential. Once it gets over land, it tends to drop a lot of that moisture and it loses its power, and it kind of dies out. So you can almost guarantee that certain areas are going to have storms, and you can predict that they will happen frequently. Enough that it affects their climate. The Coriolis effect. This is slide 21. The Coriolis effect is a result of the turning and the spinning of the Earth. If you're looking at the Earth as it's spinning from its east to west, you'll notice that winds that are blowing, those winds that are in the tropic areas are called easterlies because they blow from east to west. As they are moving across the Earth, they will tend to veer to the right in the northern hemisphere and to the left in the southern hemisphere. And winds that are going the opposite direction, or if you had a jet airplane that was going in the opposite direction, again, it will still in the northern hemisphere, it will turn or veer to the right. In the southern hemisphere, it will veer to the left. And so if it's moving from west to east, it will tend to veer closer toward the equator. If it's moving from east to west, it moves away from the equator, depending on which hemisphere you are in. This whole idea was discovered by Gaspard Coriolis, and it has helped people to understand quite a bit about how things happen in movement whenever they're using, especially projectiles and airplanes. The deflection is greater at the poles. You'll have a larger bend at the poles, while at the equator there's almost no change, no bend at all. And so it follows along the equator fairly closely. Usually the amount of change is going to be proportional to the speed that the object is moving. So it's going very, very fast. It's going to have a larger bend. The Coriolis, however, does not make it go faster or make it go slower. It does not slow it. And so it has no influence on the speed. It influences wind patterns within storms and hurricanes and contribute to the upwelling of colder water in the oceans near the coast. And here is another picture, again, up close so that you can see some of those same movements. If you would like to spend some time, just pause this here. And that's the end of our slides.